No, Balzanprices are divided into two general subject areas: literature, moral sciences, and the arts on one side, and physical, mathematical, and natural sciences and medicine on the other side. Today we start by introducing the two prize winners who belong to the latter category, that is mathematical, natural sciences, and medicine. And it is my pleasure to call my colleague Peter Suter, member of the Balzan General Prize Committee, honorary professor of medicine at the University of Geneva, former president of the Swiss Academies of Arts and Sciences, to introduce the prize winner for pathophysiology of respiration, from basic sciences to the bedside, which is actually a group of researchers from the German Center for Lung Research, who were awarded the prize for their outstanding achievements on respiratory diseases. Erika von Mutius, Klaus Rabe, Werner Sieger, and Tobias Welter, under the leadership of Sieger, joined their efforts in translating innovative research into new treatments to improve the quality of life for these patients, while also motivating and training the next generation of scientists within their common German Center for Lung Research. Peter.
Dear President of the Balzan Foundation for the Prize, dear President of the Scientific Committee, ladies and gentlemen, it is a pleasure for me and a great honor to present the laureates of the Prize for Pathophysiology of Respiration. Before doing that, a few words about how the Balzan Foundation calls for these topics, some characteristics, and also of the selection process. As you heard, every year the Balzan Foundation or the Scientific Committee selects 4 different areas, scientific areas. You heard on both sides, on the natural science side and on the humanistic side. And then selects and specifically then gives a framework for each of the domain. And as you know, one of these domains chosen, I have the pleasure now to speak about, is pathophysiology of respiration. The Balzan Foundation is an Italian-Swiss foundation, that's why this title is in Italian. I think it's very important to stress that for you. Now, the selection process has normally criteria you know very well from other scientific prizes, and these are listed here. I will not go into detail, but just tell you that these 3 first criteria are valid for all Balzan prizes. Now, for the prize on pathophysiology of respiration, we added in the scientific committee these different additional criteria, translational, which is already in the title, and then some important other ones we thought were essential overall for clinician scientists, which means, for instance, to train the next generation of scientists too. Now, we received many, many good applications, more than 20 really outstanding applications, and 3 research groups. And the Balzan regulation clearly says that also a research group can be selected if it is clear that they collaborated, not only for additional value, but potentiating the field. We had candidates from 12 different countries, from 4 continents. We had a lot of discussions, as you can imagine, to find a shortlist, and with the help of 7 specialists in the field outside the scientific committee, we finally made a decision after a long tie break, I have to say, and the winner is the group of research which was already mentioned, and you see down here again the laudatio, and said it a little bit shorter in the English way. You can see why these 4 scientists were selected. Now, who are the 4 scientists? I will just very briefly present each one of the 4. The leader of the group is Werner Seeger. He, unfortunately, cannot be with us today, so the 3 other prize winners will present their work. You see here the short summary of the outstanding characteristics of Werner Seeger. I do not want to go again in detail, but as the other prize winners, he had important merits not only in basic sciences, but also in clinical work with patients and doing the translation between the results of the basic sciences and better care for these patients. The second person in this group is Erika von Mutius. She is a pediatrician and a well-known specialist in epidemiology, understand prevention and therapy of asthma and allergy in children. And you can imagine adding collaboration of a pediatrician with this type of experience to adult physicians. Physicians for adults with asthma can have important benefits. Again, you see a few characteristics. The next one is Klaus Rabe. He is, again, as Seeger, as physician treating overall adult patients. He is responsible for a large lung clinic in northern Germany and overall a renowned specialist for lung cancer and chronic obstructive pulmonary disease, or COPD. And finally, last but not least, Tobias Welte from Hanover, and he has also some very important knowledge in specific areas, overall, lung transplantation, inflammation, infection, and again, brought the field forward together with his colleagues, thanks to this particular knowledge and expertise. So, in conclusion, that's already my last slide, the scientific committee found that this group was clearly number 1, because not only they developed collaborative research with in the head from the beginning, how can we optimize patient care? How can we develop better treatments for our patients at the bedside? They constructed an efficient network for research and competence, shared competence, in Germany, the German Center for Lung Research. They motivated and trained the next generation of scientists. As I said before, that's very important in our eyes, not only to work for today, but also to train the scientists of tomorrow. And finally, they also developed a lot of information material for the patients directly. Because in many of these lung diseases, as you know, overall in the chronic lung diseases, the patient has a very important role in the self-management during certain phases of these diseases. And this is a particular merit of this group, that they did get to this stage and develop this stage. And this is something not all scientists are really thinking about, to really empower their patients to understand and to help to treat these diseases, which can be, as you know, over several years, even lifelong in certain circumstances. Now, the three actually present prize winners will come up here and present an aspect of their research and what it is all about, starting with Erika von Mutius. They will stay up here afterwards for the discussion at the end of the 3 presentations. Thank you very much.
Thank you very much. Before I start, I want to express my sincere happiness about this incredible award and the great honor it gives me to stand up here and to tell you about the research we're doing. So we are a group, and I think this is very important that we will present together. I will start the presentation, and then Klaus and Tobias will follow, and you will get an impression overall of what we're doing together. I start with the field I most know about. This is asthma. And you can see the lung here has parenchyma, but it has also airways. And these airways can have such a shape, or worst case, such a shape. They construct because the muscle here is thicker, because there's inflammation, because there's mucus, and in the worst case, there's not much space left for the air to breathe in and out. And then these are symptoms of wheezing, whistling symptoms in the chest, and of course, shortness of breath. This is not always there. It comes in attacks. Young children, as small as babies of this size, can already have the disease, and it can go until adulthood and adolescence, and I'll show you a little bit about that. Asthma usually is thought to be allergic. In children, it's about half. Half of the children are allergic. The other half of asthmatic children are not allergic. So what do you become allergic to? You become allergic to house dust mites. These are little creatures that you cannot see with your eyes. But if you were to go home and vacuum your mattress and put the dust that you get out of your mattress under just a simple microscope, you would see that you never sleep alone. There are lots of these house dust mites in house dusts, and they cause the problem. They're still too big to be inhaled, so the problem, the allergen is here with the feces. The feces are little pellets that are inhaled, and that cause the allergy. What about the cat? The cat is a potent allergen. Of course, it's not the cat itself. What is it? It is the saliva. The allergen is in the saliva of the cat, and the cat licks its hair and thereby transports the allergen from the hairs into these environments. And some people have suggested you should wash the cat. That can reduce the allergens, but the cat doesn't really like it a lot. The next type of allergens I think you're all familiar with is the seasonal, the hay fever, like pollen from trees or from grasses. How often does asthma occur? Asthma has become, in our areas, the most common chronic condition in children. In Germany, here, but Switzerland is very similar, it's about 1 in every 10 children. If I go to a school class and I would count every 10th child at school age has asthma. And as I show you, in some of these children, this goes really from this size up to adulthood. So it's a very common problem. You can see that other countries here, it's even worse. This is English-speaking countries like the UK, the US, New Zealand, Australia. In these countries, children and adults die of asthma. We are fortunate in our areas because I have only seen one child dying of asthma, and this was because very difficult psychosocial problems. But usually in our areas, we can treat children well. But in others, it can be a deadly disease. But there's also this part of the curve. There are some places where asthma almost does not exist. Quite astonishing. So you might speculate, what is it? Is it because of genes? Because all of these have different genetic background? Or is it because they live in different environments? I don't have time to go into all potential explanations, but I will tell you it's rather complicated. And you have some environments that cause risk. This is smoking, if the mother smokes in pregnancy. This is smoking by the adolescents. This is smoking by the adult patient. This is smoking by the father of the child. This can be air pollution. This can be exposure to traffic, etc. Stress, obesity, sedentary lifestyles. But there are also protective environments. One of the best examples is here done in Switzerland by Charlotte Braun-Fahlender and colleagues, showing that children who grow up on a farm are protected from asthma and allergies. And here are the genes. They interact with these environments, and they interact with the host factor. A lot of different things in the host, the immune system, the nervous system, systemic responses, allergy, all of this interacts and decides whether a child will have a persistent wheezing or whether it's just transient and will disappear. So asthma, we have come to understand, is not one disease. It is many diseases, like in, for example, rheumatoid arthritis or others. Some children have problems early, they disappear by the age of 3, but some, look at here, start in the first year of life, and every single year they have symptoms into adulthood, and way beyond into adulthood. And then we have some that start, lose it by school age, start here, but they only lose it in adolescence, and maybe it comes back in adult years. The problem for me as a pediatrician is that I would like to recognize in this part of the age group whether this is a child at risk or whether I don't have to worry. And I can tell mom not to worry because it's going to disappear. We do not know. The symptoms in these children are all the same. And we do not have any markers, any tests that we could do to say, you really need some good medicine, or to say, look, it's going to go away, don't worry. Same thing is, there is a black box between the age group of adolescents and adulthood, because pediatricians like to talk among themselves, and in turn, an adult internist pulmonologist also like to talk among themselves. And I think this is the unique opportunity we have in the German Lung Center, that we are all together and that we can follow here from birth to adulthood. Why is this so important? Another feature is a study that has been done in Australia, where you look at lung function. 100% of how you can breathe in and out is what is normal. And you can see the enrolled patients with mild disease, with more mild to moderate asthma, and severe asthma. And they followed from age 7 up to age 40 and plus. And the remarkable thing is that this lung function stays in parallel lines. It tracks over time. So the important things that shape the way how these children breathe is before the age of 7. And we know it is before the age of 3 years that these things happen. And we know now that there are early origins of adult disease, clearly so. And this is why we have to work together. Briefly, to summarize, we have many asthma types. We don't know exactly how to disentangle those. We absolutely need to predict early which are the children at risk and to really target the therapies to those children. As a pediatrician, I want prevention. This is our best jobs in pediatrics. And I think that the DZL puts us in a unique position because it enables collaboration between the pediatricians, such as myself, but many others, internists, and importantly also basic science, because without basic science we would not understand what these different forms of diseases are. And we clearly want to carry this vision forward to the young generation. And with this, I hand over to my colleague, Tobias Welte, who will tell you the next part of the story.
Thank you very much, Erika. Again, thank you very much for giving this very, very prestigious prize to the German Center of Lung Research. It's a great honor, and in a way, it's an honor for a long time of research work we all did together. So thank you again. Grazie mille. My part in the German Center of Lung Research is infectious disease and intensive care. And one of the most threatening events in intensive care is called Acute Respiratory Distress Syndrome, RDS, which means severe acute respiratory failure, which drops down your PO2 by far. Before intensive care unit appears on the table, and intensive care unit is not a very old discipline, it's about 50 to 60 years old, all patients with RDS, more or less all patients died. If you look to the figures today, that's a big worldwide survey. We are still at a mortality rate of 40%, so we are much better than we had been 50 years ago. But we are far away from being good. I always say it's good that we are better, it would be better we are good. And there had been a lot of work to bring these mortality patterns down. One of my dear friends, Luciano Gattinoni, in Milan, he worked on mechanical ventilation and new modes of mechanical ventilation. However, now, since about 5 to 10 years, we have no further development in terms of RDS. One of the main diseases leading to RDS is pneumonia. Pneumonia is still, in numbers, the most important infectious disease worldwide, with a remarkable mortality. And if it is severe pneumonia, mortality is still somewhere between 30 and 40%. And what is the most threatening of this is it does not only affect old people. Walter Osler said in 1905, pneumonia is the old man's friend. And what he meant is, well, it's not so bad if you die in end of your lifespan out of pneumonia. But about 20% of the people coming to the intensive care and the people who die are between 20 and 50 years of age, and they are healthy. So it's one of the diseases in the young age group with the highest impact on morbidity and mortality. What makes a pneumonia patient an RDS patient? What brings you to acute respiratory failure? And Mrs. Appenzeller said it quite well. We need basic research. In medicine, it's very important to have good ideas coming from basic research to start a translational process and finally bring this to the bedside, from bench to bedside. That's our main task, our main purpose. For a long time in RDS, we looked to the mode of injury. What makes the lung and the small structures, the alveoli, ill? And we tried to overcome RDS by focusing on inflammation and balance of inflammatory processes. But we learned in the past, well, there is a problem of injury, but there's also a problem of repair. 90% of all patients with milder lung injury survive because there are immanent repair mechanism which brings you back to a healthy state. And in most of the cases, it's repair ad integrum. You are totally healthy again after some time. And so in DZL, we focused on this repair mechanism. And we tried to find out what is the driver of repair. And there are two major ones. One is stem cell, local stem cell activation, and therefore reparation processes of the lung. And therefore, you need growth factors, and this is something we were focused on. This had been first a very nice collaboration on the basic research side between Werner Seger's group in Gießen, represented by Susanne Herold, and my group in Hanover, represented by Uli Maus. And what they did is they focused on an enzyme which is GM-CSF, granulocyte macrophage growth factor, something which had been tried to be used systemically, but there had been a lot of side effects. And though we tried to use it intrabronchially as an inhaled drug to stimulate the repair of the lung. The second step was, as we finished our basic research work, we started a proof of concept study in humans. Small numbers, weak endpoint, we looked to the inflammatory process and the balancing of the inflammatory process over time, and we were able to show, yes, there is an effect. And then, and this is a major strength of the German Center of Lung Research, with money coming from the German Center of Lung Research, we started a so-called phase 2 study, which is just running, a dose-finding study in patients. Finally, we want to include 60 patients. We are just up to 56, so I hope we will finalize it in a short time, demonstrating that there's not only an improvement in inflammation, but also an improvement in gas exchange and in mortality. And if this works, it will be a real step forward. That's acute infection. My second part is chronic infection. And you heard from Erika that 50% of all asthmatics are allergic. And she asked what is with the other 50%, and she did not give an answer. Infectious disease is one of the players which are responsible for the progress of asthma. And chronic infection plays more and more a role in research. This is not a new development. Bronchiectasis and bronchiectasis with chronic pathogenic infection had been described 300 years ago. But as often, and as it is in research, it had been totally forgotten, neglected. And it came up again 5 to 7 years ago. And this was the time the German Center of Lung Research had been funded, and we started to build up a registry, prognosis, in Germany, including all bronchiectasis patients we are aware of, and sampling the data and sampling the biomaterials. And of this work, first, we published epidemiological data demonstrating that it is not a rare disease. It's a big problem, and it's increasing because it's one of the diseases which are closely related to age, which are in a way demonstrating the senescence we are all affected by. And with this in mind, we looked with different techniques to the different patterns of bronchiectasis. And I do not want to explain this here, but you can see these are totally different images. Bronchiectasis can be totally variant, different in clinical presentation, but also in diagnostic presentation. And what we learned from this is there are different phenotypes. And then we talked to our asthma colleagues. And our asthma colleagues demonstrated us, well, there are phenotypes in asthma. And one of these phenotypes is represented by the invasion of eosinophilic granulocytes into the lung. And we thought, well, if this plays a role in asthma, we look whether this plays a role in bronchiectasis. This is what happens during dinner in the DZL meetings. These are the talks. And very surprisingly, we found, oh yes, 10% of our bronchiectasis patients are eosinophilic. And then we concluded, well, if in the asthma patients an anti-eosinophilic treatment, anti-interleukin 5, which is inhibiting the eosinophilic function, helps, we do the same in bronchiectasis in our eosinophilic patients. And this has been published a week ago, demonstrating that there is a tremendous improvement of these patients by using these drugs. And with this data, out of the DZL, we now found a sponsor in the pharmaceutical industry, which will run a phase 2 study to bring it into a regulatory process and to bring it approved onto the bedside. That's what DZL is doing, talking together, combining different disease entities, creating ideas out of the box to bring basic research knowledge to the bedside, and this is all for the sake of our patients, which is the main task in between the network. Thank you very much.
Good afternoon to all of you. I'm Klaus Rabe. I'm the third one of this clutter that is incomplete as today, as you've heard. But I have also the honor, obviously, to stand up here, to talk to you, and I reciprocate what my colleagues have said. I'm deeply grateful. I'm almost as humbled as these flowers that I'm standing there. I'm still standing stand. Thank you very much. To be receiving this award on behalf of all of us and on behalf of all the colleagues that have been working with us over the last couple of years. So you've heard a lot about the topics that we've been dealing with, and what we try to tell you, obviously, is a story. And the story is, what are we doing as colleagues, and what are we doing in our research agenda? So what is on the first call in 2010 when the government said, listen, we need some form of health centers. We need to foster very common diseases. The idea was to create a network of translational science. So translational in the true sense usually means that you take basic science to application or vice versa. That is translation. But translational science, in our view, is also something else, is life cycle. Translating knowledge from early to late and from late to early. And we've heard some examples of this already: initiating of disease, risk factors for chronicity, and this is where our lifespan agenda and lifespan philosophy actually comes from. So if you think about life, if you talk about disease and lung diseases that very frequently occur in older age groups, it is a story that is in fact very, very interesting, because on the left you see these initiators. And these initiators are the ones that Erika Famuzzi has been talking about: genetic background, infections, paternal, maternal smoking, age of the parents, for example, that will then transmit into life cycle. And the life cycle is not only years that you accumulate, it's a risk factor accumulation. It's multiple hits. Because the fact that you can sit here in the audience with the age of 75 tells you a story. You survived all these hits. You repaired all these injuries. And to some end, you will actually are, if you want, a storytelling biologically, genetically, and epigenetically. And this is what disease of the lung is very much about. So if you look at this from the disease areas that we looked at, we had asthma, chronicity of the disease, plus minus infections, will lead you to some sort of convergence of a diseased lung. Now, the interesting thing is your lung function will deteriorate with age. God the Almighty gave you an organ that sort of will last until 1995, and then it becomes critical, preter propter. But basically, the story how you get there is accumulating different forms of disease entities that we have. Asthma, for example, is something that occurs, yes, early in life, but it can also occur later in life. We heard about this. And other forms of chronic lung diseases, chronic obstructive pulmonary disease, COPD, is just something that is very, very common. So what we are dealing with is an aging organism. It is the cellular basis of getting old, and it is the storytelling of your clinical diseases that you accumulate on the way. The keyword would be multimorbidity. So since we will gain something like 3.5 weeks every calendar year in median life expectancy in our ages, we have to understand what makes you survive, what makes you old, and how do you actually cope with these different mechanisms. That is part of what we do. So the asthma cohort that Erika Famutzes has introduced, it's called Alliance. An alliance is exactly, if you want, a blueprint of our thinking. So the blueprint would be that you collect individuals that have the disease. They occur in Erika's clinic, they occur in Tobias's clinic, in Werner's, and in mine. Erika would look at individuals that say, listen, you're young. I wonder what your prospectus is. I see a patient with the first diagnosis of 75, and I say, I wonder where you came from. I wonder when this happened. And I wonder why and how this disease developed in your specific way, the way it has developed. And this is why we recruit patients. We recruit patients from different centers. And if we wouldn't have this center, we would not be able to do this in a large scale, nationally. And that is why this is important, because we talk about the same language. So Erika was here. She said, listen, my black box is the transient wheezer. And who is it who loses it? And who's the one that will persist? My issue is, comes a person in my clinic that has first-time symptoms, is that new? Or is it the imprint of something that he had 50 years ago with a silent zone in between? So what we try to learn is, if I see an adult, does he have, in basic science, genetic markers, biological markers, that I could have predicted 50 years ago he takes this course? And Erika would be interested to say, in your severe asthma patients, do you find signatures that I could detect much earlier in life to be able to treat, modulate, and ameliorate these inflammatory responses to occur? And this is important because asthma and COPD alone are diseases with a prevalence worldwide anything around 10%. So think about the 7 billion people in this world and think about 7%. We have a mathematician in the room, so that is probably not that difficult. It's huge. And this is what research networks are about, asking popular, health, politically important questions, and that's what we're trying to do. The chronic lung disease has another aspect. This is something which COPD was relegated to an individual that is getting this disease later in life. But there we know that the same thing occurs. We know already now for these individuals that have COPD at the age of 60 plus, that collectively are called people that have a disease related to cigarette smoking only, that this is wrong. We know that there are very early life events that will predispose you to run this way. And there are factors that have never been looked at. Basic research will have to tell us if a child born prematurely at the age of 34 happens to be born to a mother that smokes has a much higher risk factor of so-called COPD, even though in his active life probably hasn't smoked a lot. That is a completely different understanding of a disease process. And secondly, the patients with the same disease could occur as a skinny form of a person that loses texture, weight. Skinny people, we call emphysema, or other people that are more chubby and have a cardiac problem as well. Why one of them goes the upper way and one of them goes the lower way, the secret probably is there. It's early life events that will predispose you to that, plus the infections we're talking about. You see the rhythm of the DZL? That's what we're trying to do. That's what we're trying to translate from early to late, from basic to clinical applications. And we do this for a reason. And the reason in the end is help individuals, patients, get better once they have a diagnosis. The discipline that paved the way for what we call personalized medicine, individualized medicine, is the oncologists. Oncology in the lung was a sad story for many, many years. Since 1945 until 1995, the incremental benefit of life survival benefit was 4 weeks. That's it, for non-small cell lung cancer. Since 1995, something happened. And what happened was that while we thought at 1919 all lung cancers are more or less the same, we understood through basic science that there are subtypes that can be defined pathologically. They could be sort of grouped into risk factors and different molecular abnormalities, down to targets, genetic targets, that will render you susceptible for very specific interventions, rendering some of these individuals surviving an adenocarcinoma with a certain genetic alteration for 5, 6, 7 years, something that was unheard of years before. So it's basic science that drove the recognition of the clinical phenotype that we see that translated into individualized treatment. They paved the way. In asthma, something else is about happening. We've had a long time where we said this is a functional disease, then we said it's an inflammatory disease. And the last 10 plus years where we've been contributing to this research, understood that there are subtypes of inflammation that are important. The eosinophilic subtype in the bronchiectasis. We know this in asthmatics as well. We know that their basic research gives us pedigree of inflammation that is not the same. Asthmas are not the same. COPDs are not the same. Lung cancers are not the same. And what does it result in? In asthma, it results in the same thing. Specific interventions addressing with an antibody-based strategy individualized individuals that get much better through individualized treatment. And that is what we try to achieve in the disease areas that we have. Understand the mechanisms, compare it to the clinical reality, try to find out where they have commonalities and where they are specifically different, and target the difference that we can find out. Something that would work in all disease areas. So this is our translation. Translation of DZL is from birth to the older individuals. And that is something, the way we look at it, and this is why we are sitting here and we are representing this. Asthma is for us a blueprint, and you've heard about this. We're interested in the convergence of chronic diseases into a patient that has what we call a comorbidome. A lot of different factors, and we try to understand who is getting where and how we help to survive injury in the long term. To understand endo and phenotypes, that's what we're trying to do. Why has someone that smoked the same amount a complete different course of the disease? How can we come from a larger group to an individualized biology-related interventions to improve outcome? And how can we help the field where asthma is now to develop the same thing for bronchiectasis, for pulmonary arterial hypertension, and so on and so forth? The German Center for Lung Research is a giant beast by now. It's huge. It's a huge organism. Because we've been trying to foster this, we've had a lot of help. It is growing. It involves a lot of research areas, but it is very interesting. One thing that is important, from the beginning, we understood that we had to translate it to another generation as well. We founded an academy very early on. We tried to foster talents in our areas, which was one of the shortcomings of the German medical and healthcare system. We've had phases where people were going away en masse to the US, to Japan, Now people are coming back because they understand what we're doing. That we're trying to enthuse them. We're trying to motivate them what we're doing. And we see the fruits of this. And the fruit is that we have now more than 300 Academy Fellows. We have women and men alike. We have a lot of females are coming to us. And for us, with all respect that we are getting older, we understand more and more, the older that we get, how more important it is to foster research in the young. So this is where we are going for. This is what enthuses us, and this is what we do in our universities. That is our aim. Finally, and very finally, the whole thing can only work if there is political insight that you need to shape research. And this is Annette Chavan, who is now the ambassador to the Vatican, in fact. She was the Minister of Science and happened to be my classmate for 10 years. That has nothing to do with the DZL. But she was the one with Angela Merkel that thought about health centers. And this was a good idea. And she fostered this and she promoted this for other disease areas. And it was Werner, who can't be here at present, who was there at the very early times. He helped the politics to see less in the lung is important. We thank you for your recognition. We thank you that you understand what we're trying to do. And we are humbled that we are allowed to be here. We are also grateful to the governmental and political support that we have. And I think I can speak for all of us. I think we believe that we work together while this happens because we became friends, we are partners, and we respect each other in our own territory, but we have a common goal. Thank you very much for your kind attention.
Thank you very much, all three, for these very clear, very instructive presentations. We have now a short questions and answer periods, and you are all invited to ask questions on any of the themes they mentioned, but you can also ask questions on things they did not mention, but you are interested in. Who would like to ask a question? Please. The microphone is coming. First row, the first lady.
Thank you very much for a very inspiring presentation. I'm not from the medical field. I'm an ethnomusicologist, so I'm from a completely different field. And I must say that also the model of collaboration and of opening for young scholars is what we should all as academics aspire for. So it's a wonderful model that you present. This is a question which probably was somewhere in your talks. Someone who had asthma as a child would have a tendency to have lung disease as an older adult, and what can be done to either prevent or at least lessen the chances that this would happen? Thank you.
Yes, there are some children who are at risk of continuing into adulthood. Unfortunately, the ones that are severely affected, severe allergy, severe lung function impairment, are the ones who continue. So far today, the only thing I can tell them is, well, there are two things I can tell them. Don't take up a job where you're exposed to allergens. The second thing is don't smoke. We know that a lot of the adolescents smoke, even if they have asthma. It doesn't matter whether somebody has asthma or not if we do this on a population level. But in my clinic, I always tell them, if you continue smoking, you'll ruin your life. But other than that, so far, asking them to adhere to their medication, that's a problem. Adolescent youngsters are fed up. Continue. And we have a transition clinic. So in Munich, if I have an adolescent, age 16, between 16 and 18, I hand over to my internist colleague who's going to see these kids once they are adults. And he always tells me, you didn't know, but this kid was taking drugs and he was smoking, and they never told you because mom was sitting next to him. So I think this is the way how you can hopefully improve their prognosis.
From my field, so infectious agents, mainly viruses, are a modifier by sure, maybe an initiator in some circumstances. And what is coming up now is a better and better kind of vaccination. So the main problem of vaccines at the moment is they are not effective at every life stage. There is a problem in older adults, there is a problem in young infants, and there is now a huge development of new mechanisms and producing better vaccines for more detailed viruses. So we are coming up with an respiratory syncytial vaccine, we are coming up with a new pertussis vaccine. There is a lot of development in other parts, something which affects me from the beginning of my scientific life on. There's now a new tuberculosis vaccine which looks very good, and tuberculosis, for example, in South Africa is one of the drivers of COPD. So vaccination may be one of the major preventive measures of the future.
Maybe a corollary to what you say. You know, we talked about disease states. What basic science is interested in is how do you protect yourself and survive injury? That's the point. Sort of what we call collectively, if you want, successful aging. So the DZL structure, for example, has individuals that look at cellular senescence. You can see a single cell acquiring changes epigenetically that makes them age. The good news is you can decelerate this process. So the idea coming from a cellular idea of how you sort of change the slope of life, if you want, into translating this, how you can change outcomes in disease, that is the big secret you're trying to. So we have this concept about injury, remodeling, and repair. That's what you do, principally. We also know the idea, what we call in treatment, we call this reverse remodeling. So once something has occurred, how can you reverse this process to happen? And this is where cellular science and the white coat individuals in our group, where they talk and where they have to understanding. But that's chronic diseases is there to stay. And the older we get in our populations, it's an exponential problem that needs to be understood. And in the developing countries, where they still have this ahead of them to come in chronic diseases, we should be telling them to avoid the mistakes that we've made in chronic diseases in our time. And that is the political issue about this as well.
Thank you very much. Next question, Professor Campana.
I just have one question related to what Mr. Rabe mentioned at the end, related to your biological signature. Basically, as far as I understand, human beings are all different in contrast to many other situations we have in nature. My question was, how would you manage to get an answer so specific for the various cases, you know, kind of a general trend, and which techniques would you like to use to reach that goal using big data or other things?
Yeah. Look, we are the translational scientists in that group of laureates today, and we are sort of the most practical ones. But we went back, and the methodology is, if you want, is hypothesis-free searching for data. I mean, that's what we're doing. So our keyword is deep phenotyping of the living individual, from the child to the adult, and be free, in fact, in the first place, from an hypothesis to say, listen, is there a pedigree and a pattern that would predict in the asthmatic child what the 80-year-old would actually present? I mean, that's the idea. So the DZL has people, young people, has centers, but it has platforms. And one of the platforms is a biobanking platform. So what we do is we try to deeply phenotype all these disease areas with tens of thousands of individuals from genetic information to biological information. We build up a huge repository, if you want, of biological data, and each and every one of us in his or her corner what he's trying to do is trying to find out data for trajectories to be predictive. Do we know where the golden bullet is in what technology? Is it a genetic signature? Is it a biological, biomarker, whatever signature? For some areas, we don't have a clue. Lung cancer and asthma is the role models that we have. individualized treatments are possible if you understand the genetics and or the drivers. And that's what helped us to think, we can probably make this in other diseases as well.
Well, one of the major problems, and it was for me a real surprise when I recognized it first, is we are better and better in genetics, in transcriptomics, in all these epigenetic things. And we have much better mathematics models. Mathematics is coming later on to analyze our data. But in medicine, the analysis can only be sufficient if the database is good. And what has been the problem in medicine is the database, patient data, but also the standardization of biobanking and how to win and work up the biomaterials has not been standardized worldwide. And this leads us to totally wrong answers to good questions. And this is really a benefit and a major advantage of DZL, to standardize everything besides all the partners in DZL in terms of database, biobanking, imaging standard, and so on.
Erika von Mutius.
Just a quick word. We always, as a pediatrician, we always envy our colleagues because they take 60 milliliters of blood and we take 2 milliliters of blood. So we are much more limited in biosampling, and for us, the discussion with basic science becomes important because we cannot do invasive things that you can do bronchoscopies in adults, but for children, much more difficult. And I think in this case, the mouse or some other experimental setup becomes really important.
Thank you. Is there a question just 3-4 rows behind?
Well, first of all, congratulations to the foundation for having recognized a cooperative group. This is quite rare because generally individual researchers are recognized, but cooperative groups are not recognized, although without them we would have much less progress in medicine. My question is, your group is so big, and I have seen that you have presented 2 phase 2 studies. It's a methodological question. Why phase 2 studies and not a phase 3 study, which you could do being your group so big?
That's a question of money, as always. So with the funding we have and with the funding which is possible to achieve in the German setting and also on an EU level, a phase 2 study is something about 20 million euros. That's something we can do into the DZL and into the funding properties in Germany. If you go to a phase 3, a regulatory study, this is something minimal, 100 million euros, and this is outside of what academy at the moment can achieve. So what we do is we try to bring substances into phase 2 to partner them with much more financially much stronger institutions, which mainly is pharmaceutical industry.
But it's a very good question by Franco Cavalli, who is an outstanding oncologist and knows a lot about studies of new treatments in oncology.
Yeah. No, I think it's a very valid question. And I think with the inception of this national activity of health centers in Germany, we've been asked, and I've been traveling around the world to national governments to say, listen, how do you do this and what do you do? And what I would recommend to everyone that does that is to copy one aspect of German politics in this sense. There's a lot of things in German politics you should not copy, but this one probably should. And that is that they initiated an academic industrial sort of willingness that a governmental funding would say, you researchers, you should reach out to those corporates that make drugs. You should do that. And it was not, you should not shy away from this, which sometimes in medicine is the problem. So they initiated in exactly that. So one of the remits is that, as Tobias said, you will have a molecule, you can repurpose a drug by inside, and when it comes to the big money that is involved, as a center, you're much better partnering with corporates than you were as an individual, and that's the strength of this. So what we're trying to achieve is obviously, and that was one of the remits politically on the agenda, say, German science, German clinical science, should be measured by their contributions to global drug development. That is one of the overarching themes, and I think this is smart to do. And we are at the verge now with phase 2 studies that we can get there, but we would hope to be sort of more recognized, and you are having now some representatives that know how to do this, and our job is to teach that trick to following generations to actually sort of develop this further, because we hope that centers like this one are there to stay, and we are hoping that this will be institutionalized on a federal level for the future generations to come, which I would hope that could be realized. But this is a key part of it, that you translate this into doable treatment strategies.
Thank you very much. This was almost the perfect final sentence for this first part of this afternoon. Thank you very much, you three. Thank you for your good questions. And now I'm calling on Etienne. Okay, no, Luciano Maiani.
We go now to the second prize winner for the class of Physical, Mathematical, Natural Sciences and Medicine. And the second prize winner will be presented by another fellow member of the General Prize Committee, Etienne Guise, Permanent Secretary of the Académie des Sciences at Institut de France and Research Director at Centre National de la Recherche Scientifique of École Normale Supérieure de Lyon. He will introduce Luigi Ambrosio, who was awarded a prize for theory of partial differential equations for being, I'm quoting now from the statement of the prize, a remarkable mathematician whose astonishing capacity for synthesis has made it possible to create hitherto unimaginable bridges between partial differential equations and the calculus of variation. His influence on the analysis of very general spaces is exceptional. Etienne Guise, please.
Thank you. It's always a nightmare for a mathematician who is used to prove theorems to speak after medical doctors saving lives. So I'll do my best to introduce you to partial differential equations and calculus of variations in 10 minutes, if possible. Luigi Ambrosio is a master in all meanings of the word. He's a master in mathematics, of course, but he's also a master as a teacher. He has a huge quantity of doctoral students. He's a master of the Italian School of Analysis. I'll try to say something about partial differential equations and calculus of variations. In 1677, there was a big competition between Isaac Newton and Leibniz. And Newton wanted to send a message to his competitor, but he wanted to hide his message. So he took his main contribution, of course in Latin, and decided to hide it as an anagram. And he sent the following letter to Leibniz: 6a, 2c, 1d, 13e, 2f, 7i, etc. Poor Leibniz could not understand the message, but historians of science could understand the meaning of the anagram much later, and I will translate it in modern English. The message of Newton was, laws of nature should be expressed in terms of differential equations. So I want to insist on the fact that differential equations are at the heart of science. Everything in evolution, everything moving, is governed by differential equation. Okay, now you know what a differential equation is. Now let me tell you what a partial differential equation is. In the evolution of a system, sometimes there's only one thing moving, like time or velocity, but in many cases, most cases, many things that are moving at the same time. Could be something moving in space and time, typically. For example, here you have the string of a guitar has a shape, and the shape is moving depending on time. And the equation that governs this motion is called the wave equation. It's the first example of partial differential equation. Another example could be general relativity, not the relativity that was found in Bern, but the general relativity that was found in Berlin. Space-time. The equation of Einstein is telling us about the way space and time are mixed in the evolution in time and space. This is another partial differential equation. The motion of a fluid, for example, is also a partial differential equation. This is a fundamental area in science in general. Everything in evolution is explained or understood under some partial differential equation. Calculus of variation, also created by Newton. I'm sorry, I'm French, but Newton was quite good. Calculus of variation is the following. It's a fact of nature, that nature is lazy. Nature is always trying to minimize something. Nature is trying to do things at the least cost, the least energy. This is a principle called, since I'm French, the principle of Maupertuis, the least action. Science is moving by the shortest, the most efficient way. So calculus of variation is trying to understand how to minimize or to optimize shapes or things which are moving. And the expertise of Luigi is precisely to connect these two fields of expertise, partial differential equations in connection with calculus of variation. Let me give some examples. If you have a soap bubble, you have seen these soap bubbles are kind of vibrating, and they are trying to reach an equilibrium. And the equilibrium is the shape, the soap bubble is trying to minimize the area of the bubble with the given volume. And it is a theorem that has to go to the sphere. This is non-trivial theorem. So this is classical. Calculus of variation, going back to Newton, partial differential equation is a very active domain, which is also very, very venerable. But the new thing, and Luigi is a master in this new thing, is that in the last, let's say, 20 or 30 years, people have understood that life is not smooth. Most of the theorems or techniques or tools which have been developed by the analysts in the previous centuries are adapted to very smooth objects, like a smooth curve. Corners are forbidden. And if you look around you, you will see that most of the objects that we want to understand are not smooth. For example, look at the lung. The lung is something very complicated, very fractal, as we say in mathematics. But many things are not smooth, and there was the necessity to create new tools, new mathematical tools, to do analysis, to do calculus of variation, to do partial differential equations in objects for which the previous tools were not efficient enough. And Luigi is, no doubt, one of the best experts in doing analysis in non-smooth domains. Let me give you some examples. Traffic jams. You have a city, many cars are traveling from place to place. Well, a city is not something smooth. It has roads everywhere, and trying to minimize the traffic in a city is something that is called optimal transport. And thanks to Luigi, he can solve the problem of cities, maybe. So optimal transport has been created in 1746 or something, if my memory is correct, by Monge, with military motivations, has become a very powerful, a very important domain in mathematics. Luigi is one of the best experts in this topic today, once again, in a very wide category of applications. You know, mathematics is not about solving a specific problem. We are not trying to solve this or this problem. We are trying to find ideas, general ideas, that can be used to solve general problems. Mathematics is about understanding the world. And Luigi is one of the, thanks to Luigi, we understand the world a little bit better. Let me finish by some additional comment. I said that Luigi is a master. He's a master in science, he's a master in mathematics, but above all, he's a master, he's a teacher. First of all, he is the director of the Scuola Normale in Pisa. I never attended his classes, but he's famous for being a top teacher, and this is sometimes also important to transmit science to the young people. So thank you, Luigi. Luigi, your turn.
So thank you very much, Etienne, for the beautiful presentation. I'm very honored and happy for this award. I'm very grateful to the committee, particularly because the list of previous winners, particularly in mathematics, contains many of my mathematical heroes. So I'm very happy to be inside this list. I think it's difficult for a mathematician generally to present his work to a general public. I will do my best. And in doing my best, I think it's a good idea to start really from optimal transport theory, which is a very fashionable topic by now, very important, as it was mentioned by Etienne. And so let me start. Well, first of all, optimal transport is one of our main research interests in Pisa. We organize a meeting, a very international meeting, every 2 years. This is the poster we had, the meeting we had last year. This is Piazza dei Cavalieri, the main site of the Scuola Normale. And also I want to display the first 2 pages of my research project, the research project which will be funded by the Balzan Foundation. And as you will see in the table of contents, I have made 3 paragraphs: optimal transport and partial differential equations, optimal transport and metric measured geometry, optimal transport and machine learning. And at least for the first 2 topics, I will try to give you a flavor of what is optimal transport, what are the connections with so many other topics. Also, I want to mention that I will mostly use these funds for giving 4 postdoc positions of 2 years. And of course, the main site for the research of these postdocs will be Pisa, will be the Scuola Normale. This will be the major part of the funding. All the rest will be used for minor things, conferences, small funding for travels, and so on. Also, I want to present, I try to involve some of my collaborators in this project. One is Giuseppe Savarin, a very important collaborator for me, which is a main expert on the theory of gradient flows. He's in Pavia. Then Simone Di Marino. Simone Di Marino is a former student of mine. Now he's associate professor in Genova. And Pierluigi Contucci is an expert in statistical physics and based in Bologna. They will be the main collaborators in this project. And so the index of my talk more or less already appeared in the presentation by Etienne. I think I should put optimal transport into the more general perspective of optimal transport, of calculus of variation. And I will explain a little bit what is calculus of variation, the classical calculus of variation, by some examples. Then we will move really to optimal transport, the so-called Monch-Kantorovich problem. And maybe I will illustrate also some variant of optimal transport, which is the so-called branched optimal transport. And then maybe in the last part, I will try really to explain why, in my opinion, this theory reveals to be so fundamental, so connected to many other mathematical areas, to many other applications. In some sense, quite surprisingly, because this is a discovery which goes back to 20, 25 years ago, more or less, while the problem of optimal transportation was raised by Monge in the years of the French Revolution. So this problem, in some sense, has been hidden, has been under the carpet for years, and as I will illustrate, only recently has been rediscovered. Okay, what is calculus of variations? It is a branch of mathematics which goes back to the 17th, 18th century with seminal contributions by Fermat, well, also Newton, as Guy mentioned, but let's say the modern theory really started with the work of Euler and Lagrange. And what is the question? You want basic starting, let's say, from basic physical principles, but also starting, as we'll see, from really practical questions. You want to study complex maximum and minimum problems. I think you are all familiar with thinking to high school studies with variational problems involving one variable. So you have this plot, and you look for the local maximum, the local minimum, the global maximum. But then immediately you can move to more complicated problems for which you don't have an obvious geometric interpretation. For instance, a classical problem is among all polygons with a given number of vertices and a prescribed perimeter, you would like to find the best one. And the best one for you is maybe enclosed in the maximal area. So take, for instance, this picture. And let's say that L is the perimeter of this picture. Well, in this case, it is easy to understand that this is not the optimal solution. If you try to squeeze it a little bit, the perimeter remains the same while the area increases, right? So you may think that the region with the maximal symmetry is the best one. And indeed, this guess is correct, and it's not so difficult to prove. The best solution, the best region, the best polygon, given the perimeter, is really the regular polygon. But then we can make things more complicated. Already this is more complicated because you need 2n variables to describe your problem. You don't have one variable, you have already 2n variables because for any of these vertices you need 2 coordinates. But then actually, this is the discrete version of a classical problem, which is called the Dido problem, or the Isoparametric problem, which was already mentioned by Etienne. And the origin of this problem goes back to a legend. The Phoenician queen Dido obtained from a local king as much land as it could fit in a ladder of an ox. But Dido was very creative, decided to cut this ladder in very thin strips, and she tried with this very thin strip to enclose the maximal possible area for his population, for her population. So the problem in mathematical terms becomes, given a total perimeter length, find the planar region with maximal area among all those with this perimeter. You see, it's very much related to the previous problem, but now we are considering all possible shapes, not only polygons. And then there is here another fundamental mathematical challenge. How can we study these problems which basically involve infinitely many variables? Because to describe a shape, you need infinitely many points. And the history of this problem is quite important for the development of modern mathematics. Well, you know the solution on the plane is the circle, but you can raise the problem also on the three-dimensional space. You just replace enclosed area by enclosed volume, enclosed perimeter by surface area, and the solution will be the solid ball. But then you can do this even in any number of dimensions. I mean, your physical space could have any number of dimensions, and then the complete solution to this problem came, even if this problem is classical, 20th centuries, the modern solution to this problem came only with the work of Ennio De Giorgi in 1958. And let me spend one slide about him, because probably without my meeting with De Giorgi, I will not be here. He has been my teacher. This is a mathematical conversation. I think I was more or less 25 at that time. And De Giorgi has been professor in the Scuola Normale for almost 40 years. So let's go back to the isoparametric problem. Well, you could think that this is a kind of a mathematical abstraction or a mathematical game, or you might think that physically the solution is obvious, more or less by the argument given by Etienne, because a soap bubble tries to minimize its surface area because of surface tension. The enclosed volume is constant because at least approximately there is no transfer of air between the inside and the outside of the ball. You might say, well, after all, the solution is obvious. You don't need any mathematics to do that. Well, but there are immediately many other problems related to calculus of variation whose solution is not so obvious. Let me mention, for instance, this problem, the so-called Brachistochrone problem. The problem is you want to design a curve, let's say from A to B, in such a way that a material point rolling without friction from A to B under the action of gravity moves from A to B in the fastest possible way. Actually, and then you ask yourself, again, this is a calculus of variation problem, which is the best curve to do this job, to have this point move from A to B as quickly as possible? Well, of course, not the segment, again, for intuitive reasons. On the basis of a kind of intuition, Galileo thought that the optimal solution was the arc of a circle, but in this case, intuition can't give you the real answer. Really, to get the solution, you really need mathematics. And actually, the solution, which was devised first by Johann Bernoulli by a beautiful analogy, is the arc of a cycloid. So to discriminate between a circle and a cycloid, you need calculus of variation. You need advanced mathematical tools. Okay, so this is more or less is a nutshell the history of calculus of variation. Well, then in the mature era, it came with the work of Euler and Lagrange, with the work of Hamilton, and now we have, after this contribution, the modern calculus of variation, which, for those of you who know a little more mathematical physics, can be phrased in terms of minimizing an action under some constraints, where this is the Lagrangian. So this is the classical calculus of variation, 18th, also 19th century. So now let's come to the optimal transport problem. Sorry. Yeah. So what is the optimal transport problem? Well, the theory begins with a very famous memoir presented by Gaspard Monge in the years of the French Revolution. This is the title. And informally, the very practical problem raised by Monge is this. He really had in mind a practical problem, not really a kind of law of nature. He really wanted to solve a practical question. So we are given a pile of material, of soil, let's say, and you are given a hole, remblai, and the question is, how can we move the soil from the pile to the hole doing the minimal work? Maybe the only really physical term in the original problem of Monge that he really meant work in the sense of physics, like a force or weight in some cases times this mass, in some cases times the displacement. So this is the first page of the famous Memoir by Monge, where really in the first page he explains very well what is the problem. And well, you can visualize this with a picture, right? So you have this pile, you have this hole. Maybe you decide to take this piece of the pile and to move to this piece of the hole. You have a kind of small truck and you do many travels. And then the transport cost will depend on how much mass you're moving from one place to the other along all these travels. Mathematically, this can be expressed in terms of an integral, but this is not so important for the discussion. So the integral involves the mass and the distance that you're doing in moving mass from x to t of x. Well, the story of this problem is very interesting compared to the classical calculus of variation of Lagrange and if you want to also classical physics. Because this problem has been basically forgotten for centuries. My explanation for this is that basically there was no mathematical tool to study this problem until the 20th century. So the first mathematical milestone to study this problem came in 1941 with the work of a famous Russian mathematician, Kantorovich, who, by the way, has been the first mathematician to get the Nobel Prize in economics. The second one has been John Nash. And in his work, Kantorovich introduced many fundamental new ideas. First of all, a new and much more flexible way of transporting mass, and also a more mathematical idea, which I will not explain, which is the so-called duality. But these new ideas were sufficient to rediscover, in some sense, optimal transport theory, and to have the blooming of the theory in many, let's say, more applied fields like statistics, linear programming, optimization, and also probability to some extent. But then it happened a second revolution to which Etienne alluded before. Let's say this goes back to the last 20, 25 years ago. This is quite interesting because more or less independently, different people around the world with different, also with a slightly different perspective, realized that optimal transportation could be important for other fields. And the pioneers have been Robert McCann in Canada, Jan Brenier in France, and Felix Otto in Germany. And then, thanks to all this independent idea, the theory propagated to many other fields of pure and applied mathematics. And I will try to explain a little bit what happened. But before doing that, maybe let's get a little more insight about this problem by looking. Let's say we move from the continuous version to the discrete version, which is much easier. So let's say that we are given in the plane n red points and n blue points. Let's say in this picture we have six red points and 6 blue points. And then you can imagine that the optimal transport problem is a kind of marriage problem. You want to marry any blue point to any red point by minimizing what, again, is a problem in calculus of variation. You look for the optimal coupling, or if you like, a marriage problem, but minimizing the sum of distances. So what in the marriage problem is the affinity between potential partners, in this problem is the distance. You try to minimize the sum of distances. And this problem becomes also quite interesting in statistical mechanics. For instance, when you study a huge number of points, this is a kind of simulation. Of course, the computation is almost impossible, an explicit computation when the number of points becomes huge, but you can run numerical simulations, and for instance, this is a numerical simulation of the marriage problem in this kind of picture. So you see that the situation is very irregular. Sometimes you really go to the nearest point, sometimes not, because you have to marry each point to another point. And also, well, this is a good example why optimal transport theory is so fundamental. It's so fundamental because it has a lot of variants. For instance, an important variant which is connected to the so-called Steiner problem is this one. So in the Steiner problem, instead of connecting colored points, you want to find a connection between a given set of points without any color, without any prescribed color. And then in this case, you want to minimize the total length of the network. And in this case, what happens is interesting because you have to devise new points that were not given to you a priori, which are called Steiner points. And this extension to of the theory gives rise to the so-called branched optimal transportation. So in the branched optimal transportation, instead of transporting mass in this way, again, you find out a kind of intermediate points where the mass will be split and delivered separately. We call the two ways of transporting V transportation versus Y transportation. And of course, this kind of branched optimal transportation, here I make a very small connection with the previous lecture, are ubiquitous in nature. This is the way of transporting mass from a point to a continuous distribution, so to speak. This is a river, this is the picture of lungs. And this can be described also a little bit in mathematical terms using transportation models, because also in this situation, you really need to transport something. So let me close now. I'm using really the last minutes to try to explain why optimal transport is revealing to be so fundamental. Well, this is a list of research fields which have been influenced by optimal transport problem, by optimal transport theory. Of course, basically all these fields existed, have been created independently of optimal transport, but they have been influenced by the theory of optimal transport. In particular, I have been working on, and this is related to the motivation for my prize, on connections with partial differential equations, but I have also been working on the theory of the geometry of metric measure spaces. And in my research project, I want also to explain some emerging connections, to study some emerging connections with the machine learning. So maybe the reason, maybe this is the most abstract part of my lecture, but I want really to explain this point. Maybe the reason can be explained in these terms. Let's say that you have two probability densities, which are plotted here. Let's say a probability density which is more concentrated here, and you want another probability density which is more concentrated here. I have plotted them together. And then you are given the problem which we call in mathematics of interpolation. So we want somehow to move continuously to find a path between these two probability densities. Let's say a continuous path maybe indexed by time. Let's say in continuous time, from time 0 to time 1, you want to move from this picture to this picture. And then there are 2 points of view which are in competition, which both of them are fundamental. It is important to relate these 2 points of view. Let's say the most classical point of view, which goes really back to functional analysis, is that you understand that the densities as 2 single points. So the densities are just 2 densities, which of course live in an infinite dimensional space, because the space of probability density is infinite dimensional. And then, but in this infinite dimensional space, you think that you have 2 points, and you simply connect these 2 points by a segment, which is what you will do in R2, in R3, on the plane. This is one point of view. But instead, the point of view based on optimal transport is a different philosophy, really complementary. Believes densities as clouds of infinitely many points. So you really think that probability density in a more fundamental way is a kind of random point, or if you like, of infinitely many random points, distributed according to the densities. And then these points live in a finite dimensional space. And then you move these points again with the continuity. This corresponds to another way to interpolate between probability densities. And this can be illustrated by pictures. I asked to Gabriel Perret, which is a famous expert in Paris, in the École Normale in Paris of optimal transport, and also of computational optimal transport to use these 2 slides. For instance, using this philosophy, you have a very good way to interpolate between pictures, even when the pictures are very far from each other, following this philosophy. And also this inspires quite different numerical schemes. I said that Euler and Lagrange are very much connected to calculus of variation, but actually they separate when you think to these 2 philosophies. The philosophy related to optimal transport, I would say, is the Lagrange philosophy, while the other philosophy is related to Euler. Both are very important. I don't want to diminish the role of any of them, but let me say that both inspire different ways to simulate, for instance, to emulate a partial differential equation on a computer, are the so-called Lagrangian schemes and the Eulerian schemes. Okay, so let me close explaining, I think I have the last 2 slides, I'm close to the end, to explain where the link with partial differential equation appears. Well, it appears because, for instance, you have a very practical problem that you want to minimize a function. Let's say that this is the plot of your function. This is your starting point. In this ideal scenario, the so-called energy landscape is convex, so you have a unique minimum point. This is a quite ideal scenario. And then what you do in this situation, you do a gradient flow. So you move in the direction opposite to the gradient of your function to go as quickly as possible to the minimum point. The function is typically called entropy in the applications. But now, what has been realized is that this geometrical picture, after the work in particular of Felix Sotto, applies, but to apply this, you really need optimal transport to many more partial differential equations. So many more partial differential equations can be described as gradient flows, and then you recover really a kind of geometric description of what happens. This is the typical partial differential equation that can be studied by these methods. It describes the evolution, as Etienne was saying. It is important, particularly in PDE, to look to the evolution, to the time variable. So you have a probability density which evolves in time. So the derivative with respect to time of the probability density is given by this formula. I don't need to explain what this formula, but I need only to say that this term in the formula takes into account diffusion effects. This term in this formula takes into account transport effects, for instance, the action of an external force, And this term in this formula takes into account the interaction. And it is clear that these equations are ubiquitous in mathematical physics, also, for instance, in mathematical biology, precisely because we want to describe effects of diffusion, transport, and interaction, right? And actually, my work, I've been working for several years on this, and eventually we published this book, which originated by a course I gave at the ETH in Zurich 15 years ago. And then let me just close also relating a little bit to what Etienne was saying about no smooth calculus, why sometimes we need to deal with objects which are not smooth, and why we need somehow new tools in differential calculus. Well, this originated from a work in the 80s by Chigger and Colding. They were studying limits of manifolds. And actually, the limits were taking place in the sense of a topology introduced by Gromov, which is also a former recipient of the Balzanprice. So what is the question? You study limits of spaces, different spaces which eventually generate new limit space. And then many phenomena can happen. For instance, in this case, you are generating a kind of neck pinch singularity. But for instance, you might have also other phenomena like a change of dimension. So you start with a torus, with a kind of dumbbell, and in the end you will find, because one dimension shrinks, in the end you find a one-dimensional space, while we are starting here with a two-dimensional surface. And in general, by taking this phenomena, you will find very complicated spaces with many singularities, different dimensions, and so on, corners, and so on. And then, in order to develop this program, I just want to give you the flavor or the idea. We had to collect several fields, the notion of heat flow, the notion of ordinary differential equations associated to no-smooth vector fields, optimal transport, and actually last year when I gave a talk at the International Congress of Mathematicians, I was precisely speaking about this part of my research, which will be also part of the research funded by the Balzan project. Okay, so I think I am done. I leave you some links if you're interested into these classical themes of calculus of variation, Brachistochrone, the Isoparametric Problem, and also let me mention also a beautiful paper by Alessio Figalli on the Untitled Transport Problem. This is a beautiful survey paper. You could have a look. Thank you.
Thank you, Luigi. So this is a unique opportunity for the room to fill the few gaps in your mathematical culture. So do not hesitate in asking any kind of question about mathematics, about connection with other fields. Who is asking a question? Yes.
Thank you very much. Here am I. I suppose that your transport theory and applications into mathematical problems also have some strong, promising applications in technology and, say, information theory, etc. Could you comment on what you consider to be the most promising ones?
I don't know. I think it's difficult to... So, for instance, for sure, now there is a very strong interest in applications to image processing. Is revealing to be very, very strong in this is particularly the French school of Gabriel Perret. First of all, they have devised an approximation of the optimal transport problem, which is quite much simpler to compute, because the original optimal transport problem is very difficult to study from the computational point of view. It's very complex, but it has been found an approximation which is called Entropic Approximation of the Attendant Transport Problem, which is very successful, and some simulations are very, very impressive. On the more theoretical side, more or less I said, I mean, it reveals its fundamental character, even for instance in understanding what is the heat flow. The heat flow is a very classical equation in mathematical physics, and now can be interpreted as the gradient flow of the relative entropy with respect to a distance, which is not a flat distance, but which is a distance related to optimal transport. I would say this is a very fundamental contribution for many areas of mathematics. And well, now there are all these emerging connections with machine learning at many levels, because of course machine learning has to do with discrete models. It's a discrete problem. But there are several works by several people, Montanari, Gross. There is a large community now trying to relate these discrete problems to continuous one, which is the typical phenomenon also in mathematics. When a problem becomes mathematically untractable because it has a very large number of dimensions, you try to understand what is the continuous one. As I said, this is also statistical physics, right? And so there are many emerging connections also in this direction. So I think it's quite difficult to say what will be the most important application, but I see many of them. Yeah.
One question here.
I am an economist, and my professor of mathematics said to me that the best economic mathematician is more or less equal to the worst mathematician. So since now I hope that Luigi Ambrosio will have the patience to listen an economist who is not a mathematician after all. Kantorovich is very known among economists because linear programming. And what do you think about Pontryagin, who has done remarkable works also applied to economics, optimal contour theory, path, dynamic paths from one to another path under constraint and all these things. Both were Russian. More or less, they lived in the same period. One has got the Nobel Prize in economics. Unfortunately, there is no the Nobel Prize in mathematics, as far as I know. There is some similar prize. But I always ask it to myself, why Pontryagin hasn't got the Nobel Prize? Because this dynamic, the path from one dynamic system to another under constraint is enormously important in economic analysis. So it's just maybe a naive question, but I think it's not naive at all. Finally, as you know, another mathematician has done quite a lot for economic analysis, John von Neumann, who wrote the first dynamic model, who has been, after all, the basis of more or less all the multi-sectoral dynamic models in economics. So if you have any comments, please let me know if I have said something quite odd. Thanks.
No, I completely agree. And, you know, sometimes it has to do with the committees, and it's very difficult to give an answer. I should enter into... I can reply with a joke about the Fields Medal. The Fields Medal, to some extent, is the Nobel of Mathematics. And someone says, well, the list of winners of the Fields Medal is impressive, but it is also impressive the list of those who didn't get it. You see, for instance, the Georgi, for instance, Nash, and you know, sometimes it's a matter of, particularly for the fields, this applies because, of course, there is an age limit. If you miss it, you miss it forever. But of course, I am very well aware of the contribution of Pontryagin. And also going back to von Neumann, this is another good example because, for instance, Nash got the Nobel Prize in economics for the theory of non-cooperative games. His notion of equilibrium is, of course, very important, but it is based on the notion of mixed strategy, which is von Neumann.
So, you know, and so I can't say more than this.
So maybe we could add, maybe, I'm not sure, that when Pontryagin was possibly could get the Fields Medal, it was the Cold War. And I believe that at the time, the Fields Medal was not only completely mathematical, there was also some political issues behind the decision. So I know some in the list of people who did not get the Fields Medal, I know some Russians who did not get it for political reasons. And also I believe that the Pontryagin's contribution to control theory was obtained when he was above 40 years. Question? Yeah.
I was wondering to ask you about the competition between computer simulation and an analytical approach without using computers.
Yes.
Which area do you see? Is there going to be basically a connection?
Well, I don't know. Of course, all these problems are immediately so complex that you will never find a solution in closed form already when the number of points is 5 or... so I would say the interplay more or less is the usual one. The interplay is interesting in both directions, and continuous model help you in the understanding of discrete models, but discrete models are also very important by themselves, and it is important to optimize them anyhow, so independently also the continuous models. So I don't see any specific aspect in optimal transport. I would say this is the usual interplay between computational methods and continuous functional analytic methods.
Any other question? Would you qualify yourself as an applied mathematician?
Well, no, but I could reply also in this case with a joke, because this is very country sensitive, as you know.
Sure.
This definition is very country sensitive. I know that in France I am considered an applied mathematician. So
Okay, thank you very much. Thank you, Luigi.